Hi, I like cheating at programming, and today I'm going to show you my cheat mode for creating web APIs. So I'm Erlend. I write Haskell microservices when people aren't looking, and I know the weekend has actually begun, so this will be a short talk, and I will save you from all the gory details. Those are super interesting, though, so if you ever meet me later, just ask, and I'd love to explain. So just a warning at first, there will be Haskell. Don't run away. Haskell is not scary. I come in peace. And there's actually been quite a few really good functional programming talks here at NDC, which is fun. So lots of F#. Scott Wolaskins, I hope that's his name, more or less. Talk on domain modeling in F# was awesome. You should really see it if you didn't. And yeah, has anyone here actually used F# or something? No? Oh, yep, okay. So you'll recognize some bits. So first, I actually spoke at an Elm conference last weekend, and I just mentioned in passing that I needed a backend right now at some point, so I wrote it in Haskell, and people came up to me after and said, that's really, well, surprising, because that's really not how we imagine Haskell to be. Because for some reason, this is what people imagine, like Haskell being, which, well, I mean, it's kind of cool that people think I'm smart when I write Haskell, but I have an actual picture from work, and this is much more close. And I actually really mean this, and we'll get back to this. But let's get to the point. So Servant is a library ecosystem for building web services, and it's really, really amazing, and I really mean it when I call it a cheat mode. So more precisely, it is a type-level domain-specific language, and it's a family of libraries for using these API types. So type-level language probably sounds quite cryptic, but let's look at actually what I mean by type-level. So there will be lots of hand-waving through this explanation, and if I'm not actually waving my hands, just imagine I'm doing that, because it's yeah. That will, we're not staying here all night. I promise you a short talk. So the value level you all know, that's familiar. That's where your variables and your functions and constants live. That's everyday bread and butter programming. And we're used to these values having types. That prevents us from mixing them up and stops some classes of errors from happening at all. But if we look at types as well, it looks like they too kind of have types sometimes. So why do these lines probably make you a bit uncomfortable? Well, it's not, well, you're tempted to say well-typed. List takes one type argument, not two, and map takes two, not one. So it looks like these types kind of have super types again. And it kind of looks like list and maps are functions at the type level. They take types, string and int in the first example, and then string, well, this is wrong, and then return, let's call it a proper type that you actually take as an argument or return from a function. So let's inspect this types of types, and now I'm just throwing some Haskell at you, and just bear with me. So list is kind of a type-level function that takes a type and then returns a type. So if you give it an int, then you have a good old-fashioned type. You can return from your function, take it as an argument. You can read the double colon as has type. And map takes two types before it returns a good old-fashioned type that you can use on the value level again. And don't be confused by the arrow notation in Haskell. You can kind of pretend it says type, comma type, to type. I won't really get into the details. It's not really important here. But if we give it a string, well, then we have a function from type to type, and only when we give it, for example, a string and an int, then we have a good old-fashioned type. So far, so good. Any questions, just yell out at any time. So this kind of makes sense, but let's take it a bit further. So let's pretend we have, or we create a type called DB type, and it has two constructors, SQLite and PostgreSQL. This is kind of like an enum. And let's make a function at the type level. So it says type family, which is a really fancy term, but it just means function at the type level. So we have a function at the type level called dbFetch. It takes one of these db types and a t of any type, and then returns a type, which I know is kind of strange looking, but we can create instances of this type level function. So for SQLite, we are returning the function type file path to IoT. Again, I kind of will gloss over the details, but I mean, a file path you will understand. T is the type we're going to return, for example, and IO just means you can perform IO while doing this. PostgreSQL, let's say we take a connection pool and then returns an IO of T. And we could then write a function at the value level, and we could compute its type. So we call dbFetch SQLite user that will compute the type file path to IO user. This is kind of silly, and you wouldn't really do this, but it looks like we can manipulate types at least, and we can have type level functions take and return types. Okay, so I think that was the most maybe unfamiliar and advanced part, and the details aren't super important, but the important part is we can actually use and manipulate types alone. I mean, so let's just push this on our mental stack and get to the point. So servant, let's look at the servant language. So I talked about it as a domain-specific language at the type level, and that's exactly what it is. And as I mentioned, it's this language and library. So let's look at some examples, even though we don't really know the language at all. So this describes endpoint under /users that responds to GET requests for a list of users represented as JSON or XML. So we don't know servant yet. We haven't really looked at it. But I mean, this kind of makes sense already. There's a strange tick on the list. You can just ignore it. It just means I mean the type. I mean the list type, not the actual list, but ignore it. /users / an ID. Well, we have an endpoint under /users. It will capture an integer. We're going to refer to it as ID. And it responds to GET requests and will return a user. So, I mean, we're still just playing with types there. This is just a type alias, actually. And we can go farther. I mean, let's have a post endpoint. So under /users, if you give a request body that contains a user type represented as XML or JSON, we will respond to post request and return XML or JSON and a user represented XML or JSON. And again, this is only types, but we can kind of imagine what an actual server implementation would look like here. I mean, so it's apparent that this user type needs to have some from XML and from JSON instance, and to XML and to JSON, but again, we're only playing with the API and we're only at type level. So let's, I mean, this is, Scott talked about like almost readable by non-programmer code. This is almost readable, but we can do much better, and we'll get back to that. So let's actually look at the language. So we've already seen some building blocks, like this post type. So post is a type constructor taking, well, a list of types and type to return. We have delete. I mean, you can imagine put, post, and so on. We have a rec body type that we can use in our API descriptions. Query parameters, header. I mean, you can describe a full API at the type level. We also saw some glue. I mean, so you have the drunk happy bird combinator for like combining parts within an endpoint, and the well, angry screaming bird for combining like whole endpoints. It's kind of like an alternative thing. So that's cool and all, kind of vague, but let's build an API with this. So let's pretend we have a super simple blogging system. So you have users and you have posts. Let's just focus on the users because that's the simplest. So let's pretend we have a data type called user. It has one constructor, user. It has 2 string fields, username and name. I mean, syntax isn't super important, but anyway, and we have one endpoint under /user. You can ask for a specific user. We capture a username as a string, and we return a user, and we only respond to JSON. So if a client asks for XML, we just get a content type not supported, whatever that's in HTTP. And we also have what I guess is an update endpoint. So you can send a user encoded as JSON in the body, and we respond to a put, and we'll respond with JSON and with a user. So, I mean, this probably just takes the representation of a user, saves it, if we think as a server, and then just returns the new representation. So here I've used the combining endpoints operator. And if we had a similar API for post, we could just call our API. Well, that's just a combination of users API and posts API. And these would probably live in different modules, and you could like mix and match your API as you want. Maybe you want to expose different APIs for, well, different versions of your server. But again, we're only playing with types at this point. So, and of course, we could go further and maybe protect with dot, like our users API, while our post API is public. Kind of a weird setup here. And of course, we could just choose to version our whole API. So maybe hide everything but some versions. So here's everything just living under v1. So okay, so we have our type, but that's, well, we want to live on the value level. I mean, what can we do with a type? Well, actually, we can do a lot with a type. So the most obvious one, but not the only thing, is just, well, writing a server. So it's probably what you want to do. Not always. So a server, as you all know, is, well, it's just really, I mean, a handler for an endpoint is just taking a request and returning a response. I mean, abstractly, apart from things like routing and so on. But we have a lot more information. We don't want this kind of low-level stuff. And most of all, because HTTP is freaking complex. I mean, this is the decision tree for status code for HTTP 1.1 and 2.0. And I mean, if you read the RFCs and can do this, I mean, good for you. But this is freaking hard. And if you juggle headers and status codes and so on, I mean, one, it's hard, and you will make mistakes. Just inevitable. It's so complex. So let's try to do better. So just a reminder. So this is our users API. We have encoded this as a type, but this is really what we want to implement as a server. So the top level server type is called users server. It's a function. And you can see the type signature calls kind of a type level function called server, taking our API type. So this is one of the type level functions like the db fetch we saw earlier. And at the value level, we just say this server is a combination of a get users handler and an update users handler. And the functions are quite nice. So, I mean, the get users handler take a string representing the user name or ID, and it just returns a user type, and it can do I/O. So, and well, the update user takes a string for the ID, a new user, and returns presumably, I mean, that user after it was written to database. And I've included the implementation, but it kind of gives itself because you're so constrained at this point, which is awesome because you can really only do one thing. And the hard part has already been taken care of. That was defining the API. That's probably something you did with your teammates and so on. And the other hard part is like HTTP itself, and that's kind of abstracted away here, which is super nice. So we got a lot for free. I mean, decoding the request body and dealing with all the error cases. Encoding the response. I mean, we just return a user. We don't care if it was XML or JSON. The compiler will make sure that if we have said we can return XML, we better have a 2XML instance for that type. And validating the query. So if you take a user as a request body and it's invalid, I mean, you will never, I mean, the request will not even reach your handler because the framework is already taken care of returning a 400 bad request. So this is good. I mean, these handlers are super simple. And the hard part was really just defining the API. So while actually writing the server, that's why this is a picture of me, because it's super simple, and I really like that. But there's more. I mean, we have this type, and we can actually do more than just create a server. That's the obvious use case. So we can derive documentation from the type. So here I'm using a library called Swagger, servant Swagger. And I'm basically saying that actually what I want to serve is /Swagger UI, I want to serve the Swagger UI. I also want to serve Swagger JSON file in addition to my API. So every time I push a new version of the server and it's spun up, it will just serve up-to-date documentation, which is also nice. I mean, you could also just build the documentation and maybe not serve it from your server, but that's a detail. So from our simple API definition, we would get this, an interactive version where you can play around with the requests. This is really, really nice. It's a very, I mean, as you probably know, a fun way to play around with APIs. And always up to date, and yeah, super simple. Another thing we can do is deriving client functions. So here I'm calling write.js for API. I'm specifying that I want vanilla JS. I could have said jQuery, Angular, Axios, and I don't know what else. And this means you can actually build the client functions for, let's say, the front end at build time, which is pretty cool. So you'll get something like this, which is just plain old JavaScript, and you don't have to write it because you really don't want to. But yeah, I think there is TypeScript support. I just check now. I mean, every time I check. So the question was, is there TypeScript support? Every time I check, there are like new libraries. There are like code generator for, well, Haskell, JavaScript, C#, Ruby, Python, PureScript, I guess TypeScript, and this is pretty cool. But I mean, with TypeScript, you can take it even further, I guess, if there is support, because this is what you get for Elm. So Elm, for those who don't know, is also like a front-end language, typed front-end language. And this is actually something I use in a project right now. So I specify that I want to create, I mean, this is a jumble of code, but I mean, the important part is it will generate these decoder functions for Elm. Elm will make sure that any JSON it consumes will have to be decoded into Elm types before it can be used, because Elm doesn't have like null or undefined, or I don't know what you can find in JSON. And you probably want to do this anyway, but I mean, writing them is a hassle. It's really not fun. But if you specify your API with servant, you can get this for free. So it will generate this kind of Elm code where it has the types. It has a decoder, which, I mean, it's really simple in this case. We'll just look for a username and a name in the JSON, and then return that as a user type. And you get these query functions. So you have a get users by ID, taking a string and returning an HTTP request type, and patch users by ID for if we had a patch endpoint and so on. And this is pretty magical. So the project I'm currently working on, we actually have a backend written in Haskell, but it wouldn't have to be written in Haskell. You just need to specify the API in the servant Haskell library. And since we generate the API functions at build time, if I go to the backend and change a type, let's say that we have a person and we say that actually we don't always have an age. Let's just change age to maybe age. Maybe is an option type. And if I just compile the project, the front end will tell me all the places I assume that I have an age. And it says, actually, well, you have to now account for the possibility that the age is not there, which is pretty amazing. That feels really good when you change stuff in the back end and the front end will just tell you all the places you need to update. So that's really, really convinced me. And there's actually a lot more. There is, well, you can generate HTML, of course, if you just want to serve a web page. There is a quick check library, which is a property-based testing library. Because, of course, if you can inspect the type, you can generate random, valid requests, which is pretty cool. There is client generation for, well, C#, Ruby, Python, probably tons of other languages. I just had a really, really quick look at the Haskell package database. You can also do other cool stuff, like checking that internal URLs are correct if you're actually serving some sort of web app. I haven't done that, but that's cool. There is a servant GraphQL project. I don't know how mature it is. I haven't really looked at it. And as I kind of alluded to, I mean, you don't really have to implement a server for this to get some benefits. I mean, you don't have to convert your backends to Haskell. I've used servant several times without actually implementing a server because I just want, let's say, client functions for JavaScript. I don't want to write them myself all the time with changes and so on. And for Elm, I would probably just like specify my API with servant just to get like the generated decoders and client functions, because it's really nice to not having to do that kind of, well, boring work. So to sum up my quick version of this, so specifying an API in the type system and using that specification is actually really nice. It sounds super strange, fancy, wizardry, but it's cool stuff and gets you real benefits. And advanced features can actually make our job easier. And if you want the gory details, I gave a technical version of this talk at FlatMap Oslo in May, and yeah, I go into the type level function details behind all this, and yeah, it really depends on what you want to know, but I really want to stress the fact that you can use this without implementing your server in Haskell, and it's pretty cool stuff. Thank you.